In our last presentation, we derived the transfer function from input x of s, base motion, to the motion of the mass, y of s. We also examined two practical applications which had this transfer function. Let's now look at a base vibration example that illustrates the transfer function and frequency response that we've been examining. The systems we'll study consist of three second-order systems, each with different natural frequencies, driven by a common base vibration input. The three systems are labeled A, B, and C. A is the one with the shortest flexures, B has the intermediate length flexures, and C has the long flexures. They're all excited by the base vibration, which we'll label X. The three masses for A, B, and C are identical. We'll label the motion of the masses YA, YB, and YC. And so we're interested in the frequency response of the system with input X and with output YA, or the system with input X and output YB, or the system with input X and output YC. The main difference between the three transfer functions, between X and YA, X and YB, and X and YC, will be the natural frequency of the transfer function. The natural frequency, of course, is dictated by the square root of k over m. The m is the same in each case, but the k values will be different for systems A, B, and C. System A, with the short flexures, will be the stiffest, and therefore its natural frequency will be the highest. System C, with the long flexures, will have the lowest value of stiffness, and so it will also have the lowest natural frequency, since the natural frequency is square root of k over m. At the bottom of the page here is our mechanical system model. Our input is X, and our outputs are YA, YB, and YC. The damping is not shown in this mechanical model, but it is there. There's some small amount of damping in the flexures, but we haven't depicted it in this model. In just a moment, we'll look at the frequency response plots for this system, and you'll notice that the resonance does indeed have some damping depicted. Before doing that, let me point out that this system is exactly the same as we studied earlier in the case of the automobile suspension or the vibration isolation table. We have a base input, we have some suspension or flexure, and then we have a mass that's responding to the base input. Let's now look at the frequency responses of systems A, B, and C. The frequency responses of systems A, B, and C are very similar. The main difference is the resonance frequency. System C has the lowest resonance frequency, while System A has the highest. The second thing you'll note is that all three systems have a DC gain of 1, which indicates the base and the mass will move together at low frequency. We'll illustrate the behavior of these three systems on a single plot, and to do that we're going to normalize the frequency for the systems so that all will appear to have the same resonance frequency. Then we'll indicate the position of the input frequency relative to the system's resonance using the system's name. That is, we'll label A, B, or C to indicate. So here's our first case, and that is the input frequency is below the resonant frequency of each of the three systems. The letters A, B, and C here indicate the frequency of the input relative to the resonance for that particular system. So this is indicating that systems A has its input frequency far away from system A's resonance, while the input frequency chosen is much closer to the resonance for system C. Let's now look at the experiment. We have masses A, B, and C, and you'll notice that they're moving along with the base. The DC gain is 1 here, and the motions are in phase. Now let's look at case 2. The input frequency is now higher, and in fact is the same as the resonance frequency for system C. The input frequency, however, is still significantly below the resonance frequency of system A and system B, and therefore we can expect the mass in these two cases to track along with the base motion. Here we'll see the frequency of the base motion increase and system C go through resonance. Notice how systems A and B move along with the base. Now as the frequency gets higher, you'll notice mass B has stopped moving with the base. In our third case, the excitation has an input frequency the same as the resonance for system B, while the frequency is above the resonance for system C. The resonance frequency for system A is still above the excitation frequency, and so the mass in system A tends to move along with the base. In our last case, the excitation frequency is the same as the resonance frequency for system A. However, systems B and C have their resonance frequency below the excitation frequency. Therefore, we can expect that the mass B and mass C will move very little in response to the base excitation.